Hello everyone, welcome to part 2 of the solution to the Sleeping Beauty problem and other anthropic paradoxes. In this video, I'll go through what is the Sleeping Beauty problem, what are the different proposed answers to that question. I'll also go through what is the self-sampling assumption and self-indication assumption, how are they connected to the Sleeping Beauty problem. And finally, I will discuss the Doomsday argument and Presumptuous philosopher, which are two additional anthropic paradoxes. This video basically introduced some background information, which I think is helpful to know before explaining my solution. I recommend watch it at a higher playback speed, or if you are already quite familiar with the topic, you can just skip it. Some background on the problem first. The Sleeping Beauty problem was originally formulated by Arnold Zuboff in the 1980s. The debate really took off after 2000, after Adam Alga published his paper discussing it. Since then, there have been a plethora of articles and literatures joining the debate, and there are over 100 articles on field papers alone. Here's the experiment setup. Beauty is put to sleep, and the experimenter will toss a fair coin. If it landed on heads, Beauty will be awakened once during the experiment. If tails, she will be awakened twice. But between the two awakenings, she will be subjected to a memory wipe, so she has zero recollection of the first awakening. This means when she wakes up, she cannot tell if the current awakening is the first or the second, and Beauty knows the setup. Quite often, the question is provided with additional information. For example, the experiment starts on Sunday, the first awakening happens on Monday, the second on Tuesday, etc. But I think we can all agree the exact duration of the experiment and the exact timing of the awakenings doesn't really matter here. The important thing is there's one awakening if the coin landed heads, and two awakenings if tails, and Beauty cannot tell the two awakenings apart. So the question is, of course, when Beauty wakes up during the experiment, what is the probability that the coin landed on heads? Also, what is the probability that the awakening happening right now is the first awakening? And finally, if Beauty is told that this is indeed the first awakening, then what is the probability that the coin landed on heads? I've noticed in some videos the first question is the only one that gets mentioned. I think that's a mistake, because for any serious discussion of the problem, you need the other two questions. One possible answer is what we call the huffers. Sometimes they are called the traditional huffers or Louisiana huffers, after David Lewis, who proposed it first. The reason for this particular naming will be apparent later. According to this solution, when Beauty wakes up in the experiment, the probability of heads is half, because she hasn't learned any new information about the coin toss. When Beauty enters the experiment, her probability for heads must be half because it's a fair coin. And she knows she will wake up in the experiment not knowing if this is the first or the second awakening. And unsurprisingly, that's the exact situation she finds herself in. Therefore, no new information, no change to the probability. For the second question, what is the probability that this is the first awakening? Well, there are two cases. First, if the coin landed on heads, then this must be the first awakening. This scenario have a probability of half. If tails, this awakening can be either the first or the second. Assign equal probability to both, we get a quarter. Adding both scenarios together, we get the overall possibility that this is the first awakening as 3/4. If Beauty is told that this is indeed the first awakening, then the probability of heads changes to 2/3. We can get this result with the simple application of Bayes' theorem. To Louisiana huffers, this answer is very intuitive. Because the awakening happening right now is more likely to be the first one if the coin landed on heads. Therefore, the new information that this is indeed the first awakening increases its probability. Beside the Louisiana huffers, there's also the thirders approach to the problem. Note there are two potential awakenings in the experiment, and the current moment could correspond to either the first awakening or the second, and we should assign equal probability to them. The fact that I am awake currently means this cannot be the second potential awakening and the coin landed on heads, because if so, I should be sleeping right now. This basically reduced the probability of heads by half. And the remaining three possibilities, that heads first awakening, tails first awakening, tails second awakening, are all equal probable. So the probability of heads becomes 1/3. According to most thirders, this is also quite intuitive, because being awake now is evidence suggesting there are more awakenings overall. So the probability of tails must be higher than what a fair coin suggests, which is higher than half. It is also worth mentioning that in Adam Alga's original paper, he didn't consider being awake now a new evidence, because you are guaranteed to find yourself awake at the current moment. He argued this is the special case where updating the probability without new information is correct. But most thirders nowadays would argue being awake at the current moment is valid new information. Once we get the first question out of the way, the remaining two questions are easy according to thirders. Among the three equal probable possibilities, two of them are the first awakening. So the probability that this is the first awakening is 2/3. And after learning this is indeed the first awakening, the probability of head becomes half, which is again a simple Bayesian update. It should be mentioned that both huffers and thirders have their own frequentist models. For example, thirders would argue if we repeat the experiments many times, then the relative fraction of heads awakenings would be about 1/3 of all awakenings. Just to put a number on it, for example, if we repeat the experiment 1,000 times, there will be about 1,500 awakenings, out of which 500 will be heads. Then the relative fraction of heads awakenings will be 1/3. To that, Huffer will say, well, don't count the relative fraction based on the number of awakenings. Count it based on the number of coin tosses. If we repeat the experiment 1,000 times, then we get 500 heads, and the relative fraction is just that, 500 over 1,000, half. And that is the correct way to count relative fractions. It is very hard to argue why one of the model is correct while the other is wrong. So the frequentist approaches haven't been able to settle the debate. Just a little spoiler, in my solution I will show how accounting the relative frequency by awakenings and accounting it based on number of experiments would give you the same number based on the correct frequentist model. That's something we'll discuss later in the video series. Let's look at some counter-arguments. Adam Alga pointed that the coin toss only determines if beauty will be waken up again, so we can toss it after the first awakening. And according to Louisiana huffers, after learning this is the first awakening, the probability of heads is 2/3. So they are predicting a fair coin yet to be tossed with a probability other than half. This is obviously problematic. It violates the principal, which says if you know the objective chance of something, you should assign the probability as such. But Thurder's answer is not problem-free either. According to Thurders, at the beginning of the experiment, before Beauty goes to sleep, she knows that her probability for heads is going to be 1/3. If she believes that is the right answer, and this is guaranteed to happen, then she should believe this is the right answer for now as well. But obviously, before it goes to sleep, Beauty will give the probability of heads as half. This violates the reflection principle. And that leads to the third possible solution for the Sleeping Beauty problem, which we call them double huffers. It says the probability of heads is half when Beauty wakes up in the experiment, and it remains at half after learning this is the first awakening. So you will have neither of the two problems mentioned above. But this answer is non-Bayesian. It doesn't use the Bayes rule to update the probability when learning this is the first awakening. And double huffers tried to come up with alternative updating rules to replace the Bayes theorem in order to justify this answer. As you will expect, there are many counter-arguments against these new updating rules. In my opinion, Michael Titanbow's argument has conclusively proved that there is no alternative updating rule that can keep the probability unchanged at half. I will examine this argument in detail in a later video. One way to look at the Sleeping Beauty problem is to say there are three very intuitive statements, yet they cannot be all correct at the same time. Number one, the probability of head is half when Beauty wakes up in the experiment. Number two, the probability of heads is half when Beauty learns this is the first awakening. And number three, Beauty should update her probability using Bayes' rule when learning this is the first awakening. If you choose to reject the first statement, then you are a thirder. Reject the second, you are a Louisiana huffer. And if you reject the third, you are a double huffer. Now let's take a look at the self-sampling assumption. This is one of the two major camps in anthropic reasoning. It says all other things equal, an observer should reason as if they are randomly selected from the set of all actual existent observers, past, present, and future, in their reference class. This may seem a little bit mouthful, but really it's just describing a quite intuitive idea, that I am a typical observer. It is consistent with the Huffer position in the Sleeping Beauty problem. In particular, what is the probability that this is the first awakening? Huffers divide the case into two possible scenarios with different number of actual awakenings, and then assign probability equally among the actual awakenings. It is essentially an assumption on how to apply the principle of indifference. There are two things that are worth our attention. First, what is the reference class? We'll see later that this is a major problem for self-sampling assumption. Another thing is the part that says past, present, and future. This is some peculiar expression that we don't see very often, if at all, in normal communications. I'll explain the strangeness in my solution. The self-sampling assumption can lead to some controversial arguments, and perhaps the most famous one is the Doomsday argument. It basically says, once consider our birth rank among all human beings, we should believe our species is going to end sooner. For example, if there are two urns, one has 10 balls in it, the other one 100, and all the balls are numbered. Suppose you are presented with one urn, and you don't know which one it is. But then a ball is drawn randomly from the urn, and that is the ball number 8. Considering this, it is far more likely that this urn have 10 balls instead of 100. If you were indifferent before, a Bayesian update would suggest the probability that this has 10 balls is 10 out of 11, 10 times more than the probability that the urn has 100 balls. With the same logic, say if we have two different predictions about our future. One says we will go extinct in the next century, and the total number of humans ever lived is 200 billion. The other one says we have a bright future as a species, and we won't go extinct until the total number of human beings ever lived is 200 trillion. And then we take a look at our birth rank. Looking back at history, we know the current generation have the birth rank of about 100 billion. Then you should greatly increase the probability to the first prediction. If you were indifferent before, now its probability is 1,000 times more than the second one. The logic of Doomsday argument can be roughly summarized as, I am more likely to be the person I am if there are less humans overall. For example, if there are n humans overall, then the prior or uninformed distribution of my birth rank is just uniformly distributed from 1 to n. One thing I want to point out is, the Doomsday argument is supposed to be just a simple Bayesian update, yet it is surprisingly tricky to explain. People often resort to analogies or multiple thought experiments to get the message across. I will explain why this is so in my solution. The general opinion about the Doomsday argument is that most people think it is wrong. For example, what is my correct reference class? What is the range of observers that I should consider myself a random sample of? The argument just simply says the reference class is human beings. Should it include Neanderthals? What about chimpanzees? That will change my birth rank. What about future people who might have augmented limbs and organs? Are they still considered human beings? I mean, there's no clear logical answer to those questions, yet it will affect our prediction about the future and our probability calculations. However, having problematic implications does not mean the argument is necessarily wrong. And the leading counter to the Doomsday argument is what we call the self-indication assumption. The self-indication assumption is quite similar to the self-sampling assumption. It says all else equal, an observer should reason as if they are randomly selected from the set of all possible observers. Following this logic, the Doomsday argument is not as much as logically wrong, but rather incomplete. The fact that I exist as a human being is an evidence suggesting there are more human beings overall. This will increase the probability of the prediction where there are more human beings being born in the future. And this effect exactly cancels the effect of Doomsday argument. And the self-indication assumption is consistent with Thurder's position in the Sleeping Beauty problem. But the self-indication assumption also have its own implications that is problematic. One of such problem is the Presumptuous Philosopher by Nick Bostrom. Imagine there are two competing physical theories. One of them suggests the universe is big, with roughly 10 to the power of 12 observers. The other theory suggests the universe is much bigger, with roughly 10 to the power of 24 observers. Then, without doing any experiment or research, we should already be highly confident that T2 is the correct theory. Reason being because I exist. It is quite counterintuitive that a real physical problem can be solved by armchair philosophers. And this is not an imaginary example. It has real-world implications on physical theories. For example, there has been debate among philosophers whether the third position in Sleeping Beauty problem will confirm the many worlds interpretation of quantum mechanics. And thirders have different opinions about the presumptuous philosopher. For example, some suggest they should simply bite the bullet, others saying there's reason to refute the problem. Some suggest self-sampling assumption is not better off, it has its own versions of presumptuous philosopher, and there are other opinions about it. And those two thought experiments are not the only problems of the anthropic assumptions. For self-sampling assumption, beside the Doomsday argument, there is the reference class problem which we talked about earlier. Self-sampling assumption would also suggest two persons fully sharing their information could still give different answers to the same probability question, which violates the Allman's agreement theorem. There's also the probability pumping problem, which hints on retrocausation. For self-indication assumption, it still has a reference class problem. I've seen many people, including Wikipedia, saying SIA does not depend on the reference class. This is actually incorrect. For some problem like the Doomsday argument, the effect of choice of the reference class get cancelled. However, that's not always the case. Does my reference class include computer simulations? Should it include observers from other universes? The answer to those questions will change SIA's conclusions in many anthropic problems. Self-indication assumption also has a doomsday argument of its own, because it suggests the great filter is more likely to be ahead of us rather than before. Another problem is that self-indication assumption has a hard time dealing with infinities. But overall, I would say self-indication assumption's problem is less serious. So if you want to stop watching the remaining videos, I just want to take a pick between the two, which I hope you do not, then self-indication assumption is the lesser evil of the two. I realize this video has been quite long, despite my effort to be as concise as possible. And in fact, all the information I just covered are just the basics. There are many more positions and nuanced arguments that's impossible to cover here. The fundamental thing to take away here is the Sleeping Beauty problem is an anthropic paradox. and its different answers reflect different anthropic assumptions. Knowing this is a good foundation to understand and evaluate my solution later. And in the next video, I will explain the foundation of my answer to the question. I will see you in the next video.